Hi, my name is Mr. Bellamy. I'm a grad student at NC State University. I'm doing a demonstration for MAE 535 on reed switches. A reed switch is an electrical switch that changes position via magnetism. It's constructed of two contacts of ferromagnetic material, such as nickel alloy, and is housed inside a sealed tube constructed of glass or polymer. Inside the sealed tube is a noble gas, such as nitrogen, to eliminate corrosion or contamination. It's activated with a magnetic field, either by electromagnets or a permanent magnet. A permanent magnet, as you can see here, the north-south pole orientation will engage in two positions. You can see the magnetic field is shown in green, and it causes those contacts to be attracted to each other. Similarly, if you rotate the magnet 90 degrees, it will engage in three positions. A practical application is flow meters. One method is a piston-style flow meter where it will reciprocate axially, and there's a compression spring to keep it in its home position. There's also a pinwheel method where a magnet will rotate around an axis and become engaged and disengaged with a pulsation effect. Let's check it out. Here's an up-close view of a reed switch as I enter a magnet. It closes and opens and closes. Let's see it in a circuit. And here we have just a basic breadboard circuit I made. It's connected in line with a reed switch here in this gray fixture that you see. And it's also in series with a red LED. This is powered with a benchtop power supply at 1.8 volts for the LED, and it's current limited to 400 milliamps. I also have a permanent magnet here. It has a north-south pole axial orientation. And I want to turn on this reed switch by engaging it with this permanent magnet. As I get closer, it should turn on. Move farther away, turns off. Notice I'm off to the side of the reed switch here. Off to the side. As I go towards the middle, it turns off. Goes to the other side, turns back on. Changing the reed switch out for a more sensitive one, I'm going to use the same magnet, north-south pole, axial direction. Let's see if I can get three different positions on this one. So by orienting in the same axial direction as the reed switch, might be able to pick up one end here, towards the end. As I move it down, it should turn off, and turn back on when it gets close to it. Turn off, and turn back on. There's two spots that it doesn't pick up, there and there. Just for fun, I also wanted to create an electromagnetic field instead of using permanent magnets, which actually transformed the name of these from reed switch to what they call a reed relay. And basically, I'm using a second benchtop power supply hooked up to two leads around a coil. And that coil has about 10 turns of wire through it. And I'm going to put a certain amount of current through there and see what amount of current as well as the turns engages the reed switch. And this reed switch is rated at 5 to 10 AT, which stands for amp turns. So that's the magnetic field that's required to activate it. Let's turn on this power supply. I have currently about 1.16 amps of current going through that wire. If I move it over the reed switch, it should turn on. As we know, with a solenoid, the magnetic field is greatest in the center of the coil. We got it to turn on. Okay, let's do a little bit of math. The current we saw was 1.16 amps through 10 turns of current. It creates the magnetic field that you can see here in green. The overall length was about ½ an inch. We can calculate that with Ampere's law. The magnetic field intensity is the same as the charge enclosed divided by the length of the solenoid, which calculates down to about 913 amps per meter. The flux density is only about 1/1000th of a Tesla. It's very small. You can also calculate it with Biot-Savart law, which will be the summation of all the different individual coil magnetic fields and acting on the solenoid, on the reed switch itself. So as you can see from the plot, very similar to what we drew in class. This is an effect of both fringing, and we also saw that same effect when we were moving the coil around the reed switch, and it essentially was just decreasing the magnetic field strength due to each individual coil moving further away from it. And that concludes my demonstration for today. I hope you guys learned something. Thank you very much.